My name is Marc-Antoine Desroches, and I'm a technical architect. I've been working on video game engines for 20 years, but for the last couple of years, I've been focusing more on instrumenting the game engines and running analytics on the ton of data that is coming out of it. Just a quick disclaimer. I'm talking in my own name. I'm not representing my employer today. The objective of Micromega is to quantify the frequency and the gravity of the issues with enough context to be able to fix them without having to reproduce every single bug or performance problem that we have, right? And that's typically not the way things work, at least in the games industry, where we usually have very specific tools that will connect directly to the game instance, and they will help us debug or profile what's happening in there. Or we can have telemetry that will give us statistics about what's happening, but not enough information to actually correct the issues that we find, right? And the idea is that we refuse to choose. We need both. We need to just capture enough data so that we can make a great game. But the challenge is significant, right? Because games run at 60 frames per second, and we don't have log entries for each frame typically. That's just too verbose. But we still have tens of log entries per second. We do have measurements about each frame, sometimes tens of measures per frame, so that is getting a significant amount of data. But the really difficult part is the performance trace, like the CPU trace. In order to understand what's happening inside one frame, you need thousands of events for that one frame. So that means that you're going to be recording like this between 100 or 200,000 events per second. You multiply that by the number of concurrent users that are sending data, and you got something pretty significant on your hand, right? And on top of that, we want a single system for everything, not one system for logs, one for metrics, and one for traces. We want to be able to query all of those data streams together. So originally, this was at the very end of the presentation, but I figured I might as well just start with the dessert. So this is real-world data. The system has been is collecting data for usually we have a retention period of 90 days. Inside of those 90 days, we've collected 9 billion log entries, 275 billion measures, and not quite as many sample trace events. So we're going to see later why the number of trace events is not as high as the metrics, because there's some sampling going on, which is not the case with logs and metrics. We're just capturing everything. So in those 90 days, we recorded like almost 450 billion events, and that's a very bursty workload. We have spikes in the hundreds of millions of events per minute. But it doesn't cost us too much, right? Because compute is $300. That includes load balancing. We have a couple of very tiny VMs for ingestion, slightly bigger VMs for the daemon and analytics service, which we'll talk about pretty soon. And almost every the metadata of the data that is stored in PostgreSQL, so that's about $200. And almost everything is stored in S3. Object storage is notoriously cheap, so that's worth $500 per month for our use case. Totally $1,000 a month. Right? How do we do that? So the whole presentation is about the strategies at every stage that we apply in order to make a very efficient system. At stage one, we have a dedicated instrumentation layer that's very optimized. At stage two, we'll be talking about the ingestion service. Stage 3 and 4 are the daemon and the analytics service. The daemon will process low-frequency streams as they arrive, while the analytics service is responsible to execute the SQL queries in general, but also to process just in time the higher frequency data streams. And stage 5 is our strategy before the user interface, right? Because frugality is important there, since the whole point is to have to be able to extract value from the data without spending too much money. If we have a huge team working on the user interface, then it's not that frugal anymore. And you'll notice that, I mean, nothing in there is specific to video games, maybe aside from the instrumentation in Unreal Engine. We also have an instrumentation layer in Rust. So I think that even though you're probably not working in video games, you can probably either apply some of the logic that we found, or even reuse the code or the project for your own needs. Before we dive into the specific stages, let's just let's take a quick look at the architecture at large. First is the ingestion data flow. So data moves from left to right in what you're seeing there. We have the instrumented applications. So we have two APIs to instrument applications. The first one is a Rust library. The other one is Unreal modules that you can insert into your Unreal Engine game. Right? They both send data using the ingestion web service. The ingestion web service will take the metadata, which is information about the process and the time span about the events that you're sending. It will record the metadata in the PostgreSQL database and take the payload and write that to a string. The flip side of that architecture is the analytics data flow. So requests are coming in from Grafana or client or the Python API. They both connect using a flight SQL protocol to the analytics service. And that analytics service can access the data lake we've been describing in the ingestion part and fetch use the PostgreSQL database to know what exists, and then go and fetch the payloads that corresponds to whatever the user is querying for, and then transform that into Parquet files, put those into the lakehouse, and remember where we put that file and what its schema is, and that kind of metadata, and save that in the PostgreSQL partitions table. Let's go with the details. Stage one, the instrumentation. So because we record thousands of events per frame, we need a very optimized instrumentation library. The basic optimization we did is to make sure that the events are very small so that we can send many of them. And we keep them small by allowing events to have raw pointers inside of them. And those pointers can reference global data so that we avoid repeating the same strings over and over again, like the file names or the metric names or the function names. The instrumented threads do as little work as possible for the instrumentation part. Usually it's just sending an event, and that event will be processed in the background thread. Right? That's how we can keep the instrumentation overhead of a single event in terms of a very few nanoseconds. Like for the CPU trace events, it's about 20 nanoseconds. It's a little bit more for log entries and metrics, but because there's a synchronization overhead, but it's very reasonable. And then once we collected those events, we apply a sampling logic to whole event batches. I mentioned earlier that there was no sampling implemented for logs and metrics. There could be, it's just that in our configuration, we just record everything. But there is sampling applied for CPU trace events because there's just so many of them. And then once we decided that we want to keep a batch of events, then it's down to the serialization, which is mostly memcopy. So it's very efficient. But that means that the event layout inside of the protocol is native to the memory format of the instrumented applications. And that has an impact downstream for the rest of the system. Right? So it makes things a bit more complicated and a bit more expensive on the analytics side, but it's absolutely worth it because it allows us to record that much more data inside of the game, right? And then right before sending it, we compress it using LZ4. Thankfully, all of that complexity doesn't show up too much inside of the instrumentation code. Here's a Rust instrumentation example, right? You have your Rust macro that will record the spans. It will do different work depending on if the function is synchronous or asynchronous. You have your info bang macro there that looks like a normal logging macro, and you have metric macro that will record the request duration there. There's also the floating point version. The Unreal instrumentation library, it sort of looks the same, but because it's in C++, you have those C++ all caps macro that are streaming at you. But aside from that, it's pretty much the same. Stage 2, ingestion. The ingestion service is the simplest you can imagine. It's a glorified S3 proxy. All it does is it accepts the SD4 compressed payload. It doesn't even try to decompress it, let alone parse it. Right? It just takes that payload, puts it into S3, but right before we take the metadata about who's sending the data and why, and record that inside of the relational database. So the metadata about the payloads and the payloads constitute our data lake, which is optimized for cheap and fast writes. And then the stages 3 and 4, that the daemon service and the analytics service will bridge between that data lake and the lakehouse that is optimized for fast reads. So those two services are able to go and fetch the binary data, decompress it, decode it, parse it, make it into something useful, and then write Parquet files that represent that data. And then once we have Parquet files in our lakehouse, we just let Data Fusion execute the SQL queries on it. The daemon specifically has different strategies depending on which data stream. So as I mentioned quickly before, the instrumented applications advertised a few different data streams. One is for logs, the other is for metrics, and then there's one CPU trace stream for each instrumented thread. Logs and metrics are processed as soon as they arrive in the data lake. The daemon will catch those payloads, transform them, and write Parquet files so that they're immediately available to anybody that wants to execute queries in them. The daemon also keeps the aggregated views up to date. The aggregated views is what allows users to query multiple days of data without those queries being inefficient or scanning too much data. Right? But that daemon completely ignores any payloads that are representing CPU traces because those are just too big and too costly. And frankly, because most of the time, an individual CPU trace will not be read. Even though there's some sampling at the application layer to just instrument make sure that we're only sending the spikes, basically, when there are performance problems. Because the same problems happen over and over again, we don't need to look at them individually. I mentioned aggregated data views, so that's how we do data reduction. So you can see there. So in Micromega, we can register our own views using SQL, and then those relies on the existing views that are available by default. So in this case, we're aggregating the log entries into a log stats view. Stage 4, the analytics service. So the service accepts SQL queries using the Apache Arrow Flight SQL protocol. It's very efficient. It's based on Apache Arrow. And the analytics service, if the data is not already available inside of the lakehouse because either a previous query filled it or because the daemon populated it, the analytics service will be able to go and fetch those payloads, transform them, and write Parquet files as well. And once again, it's Data Fusion that executes the SQL queries. But we do have extensions to it to add features. We rely in part on JSONB for very flexible and relatively compact JSON-like data structures. And we also implemented the histograms so that we can accumulate histograms and then get the median or P99 values very quickly. Even though we're like computing P99 on millions and millions of frames, because it's all aggregated histograms, it's very efficient. And last but not least, I mean, what users actually see, we have 3 main user interfaces. There's the Grafana for dashboards and alerting. We have Jupyter notebooks through the Python API for data exploration and just anything really. Tooling is also built using the Python API. And we have Perfecto for secure trace visualization. You guys know what the Grafana looks like. I don't need to talk about it much. There's the Python API that's available that integrates really well with Pandas or Matplotlib or whatever you want to use there. And I don't know how popular Perfecto is in the analytics world. I'm sure that Android developers know it very well. It's a very convenient tool by Google to explore detailed CPU traces. It can handle millions and millions of spans quite easily. It's a very powerful tool. And I want to say thank you to, all of those solutions I depend on, because Micromega would not be possible without all of those open source tools, right? Big shout out to the Apache Arrow project that gave us Flight SQL, Data Fusion, Apache Arrow, and Parquet. Thanks to Influx Data, I used their Flight SQL plugin for Grafana to make our own. We also use PostgreSQL and rely heavily on the Rust community. So thanks. And in a way, I'm sort of giving it back too. So Micromega is completely open source. If you find any of this interesting or useful, please drop a star. It always makes my day. Try it out. You can use it both as a library or run the code directly, or just copy the code. Anything that you feel is useful to you, just go ahead. Open an issue on the GitHub. Tell me what's missing for you. Tell your friends and send me a quick note if you want to talk.